So welcome back. Today we're going to be continuing where we left off, talking about neural potential functions and how to learn when we have them. And we'll also begin to move into a discussion of how we can do map inference by casting the whole problem as a mixed integer linear program. So we'll actually talk a little bit about just what is linear programming, the algorithms that exist to solve it, what is integer linear programming, and how we can solve it with branch and bound. And then once we've done that, we'll kind of double back and look at how we can actually treat this map inference problem as something to be solved by a mixed integer linear program. Okay, so one reminder here that the last chance to switch between 1014 and 2618 is coming up. So I think the drop deadline is October 7th. And so I was told that you can make that switch with an appropriate sort of drop form and late add form coupled together. Okay. So what we want to think about is this notion of sort of using backpropagation in the context of belief propagation. And so I want to think about how we can actually come up with the appropriate gradients or derivatives with respect to actual factors. Okay, so these are the answers that we're going to come up with, but what I want to see is how the conditional independence assumptions that we make actually allow us to come up with those. So what we have is a problem where, actually I guess it's worth just making a quick note about where we left off last time. So last time we had said that we could think about a computation graph that ties together our use of belief propagation and log likelihood into one sort of unified picture of a loss function. Okay. And so, in fact here, I guess it's probably useful to just have a copy of this. So, what we can conceptualize this as is a setting where we're basically treating the entirety of sort of the middle and right part of this picture as itself some black box loss function. So pictorially, what I mean by that is everything in this box we could think of as defining for us. So here's actually also a great. I didn't start with Q&A, but I'll start right now in Q&A. So one thing that came up in office hours is I had written the loss function L of theta given x, but we actually kind of noticed that's not quite right. Really, we can't compute the loss without having both x and y. Okay, so if you look at the actual leaf nodes in this computation graph, they're the theta parameters feeding into the LSTM. Then the x parameter, the x feature is representing our example. And then the y vector representing our ground truth also needs to be fed in to the likelihood here. And so maybe I should be a little more careful and say that the box that we're talking about here, that is our loss function, is really everything except for our leaf nodes and our computation of the actual potential functions. And so everything inside this box is what we're thinking of as this loss that is a function of theta x and y. And so the question is, if we want to run belief propagation, what do we actually need for this loss function. Did I say we want to run belief propagation or backprop? Did I say belief propagation? Ah, that's why you're all like staying there. What is he talking about? See, this is the problem with names that sound too familiar, are too similar to each other. So if we want to run the backpropagation algorithm here, what do we need to run the backpropagation algorithm if we're going to use this as our loss?
Derivatives.
Of what specifically?
Well, you get the log likelihood, and you also need derivatives of like the propagation box.
Upside with respect to the.
Yeah, so it feels like, gosh, we need like all of these little derivatives along the way. Okay, I'm going to make things simple for you. So backprop here, we'll just use the derivative, or the gradient of, let's write it as a derivative, a vector derivative. So it's going to be the derivative of the loss, L, which is a function of theta, given x and y. And it's going to be with respect to z, right? Which is, you could just say a gradient with respect to z of that loss. So if we can come up with this, right, where z is, I mean, it's not just one number. Z here is a collection of numbers representing all the numbers that we need to define those potentials, right? And if we can get those numbers, if we can get those derivatives with respect to z, then we don't really have to worry about the internals of exactly what belief propagation is doing. Okay. So what we can do instead is just write down the log likelihood of the ground truth. Okay, so here we're going to be thinking about the actual derivative of a potential function. And we can actually do this sort of one of two ways. The way that I want to start with here is actually to take not the derivative directly of the potential function, but rather to work with like one element down on the stack. So if this is some element called z here, which is the output of the x, then we could say that before we apply that x, there's a sense in which that z variable is sort of written in the wrong place here. So if this is a proper computation graph, we're saying that the function is x. So the thing that is the output of x we'll call z. And then we could call the output of the LSTM z prime. So z is x of z prime. And what I want to actually work with today is the derivative of the loss with respect to z prime. Okay? And notice here we have that z is actually equal to the potential functions. It's a full definition of them. And z prime here is equal to the log of the potential functions. Right? Yeah, question.
So the potential function will basically tell us the this potential at every y, right? Every possible y.
So
Like this would be like a vector that won't have any correspondences to y, or would it?
yeah, so that's right. So let's actually draw a picture of just what these potentials are, because I think that'll help clarify. So let's suppose we have a sentence like time flies fast, and so we're going to have some black box that is an LSTM. Okay, and just for simplicity, we can draw that as some recurrent function on that sentence, and maybe just if we wanted it to be like a more interesting bi-LSTM, it could go both ways, and then we could have as output vectors these values, which we're going to call z prime. So now, what we want to do is we want to have a factor graph, and the factor graph is going to have variables y1, y2, and y3, and attached to it are factors. Okay, but let's make these factors sort of larger than life here, and let's say that in this example, each of the y values are binary random variables. So for this example, we're going to say that the unary factor on y is itself going to have two little cells, and on y2 and on y3. So to get from z prime to what we're calling z, which are the actual values of the potential functions, we're going to apply x to the values of the output of the LSTM. So at this point, maybe we should say that we might also want transition factors, and if we did that, those transition factors would be for binary variables. They would be these little 4x4 grids, right? Connecting up our pairs of random variables. And so maybe what we have here is that there's some other sort of complicated function of the LSTM that gives us back these little matrices. And how do we get that matrix? Well, maybe we just concatenate together these two and pass them through a linear layer to get something of the right shape. And so then the same thing can happen here, where we pass these through x to get back our potential functions. Okay. So here we have this picture of z prime and z, where we can think of these as roughly the log of the potential function or the potential function itself. Okay. But we're sort of we're sort of being flexible, shall we say, with our notation by saying that this z prime is some combination of all of these put together. Okay, so it's some like rich mathematical object here. Okay, so any questions about our computational graph setup? Yeah.
Where are the outputs of like that graph? Like is it like after you go through like the y nodes that gets sent to the one like?
So the outputs of this graph. Oh, I see. So by that, do you mean like where do we get the, so I haven't like combined this picture with that one. Is that what you're asking? So, so what the picture below here is showing, this example for binary random variables, is just showing how we could have some LSTM layer that is giving us back values that we can use for the factors. Okay, so once we have this notion of the LSTM output giving us values for factors, now we can go back up to our first picture. Okay, so in our first picture, the values of those factors are right here. And so when we run belief propagation, we have values for all possible assignments to y. Because the factors express the full probability distribution over all possible assignments to y. And so what we get out of belief propagation are marginal probabilities that tell us the probability of each y variable taking on its different possible values. So finally then, we can use those marginal probabilities or this partition function in combination with y, the ground truth, to actually compute the likelihood of the data.
Can you explain what goes into the belief propagation? There is Z that Z is equal to the potential, but from there Z is going into a potential function and then the output of that goes into.
Yeah, sorry, that's I guess confusing. So again, let me correct this slightly. So I guess what we're saying here is really in our picture, Z is the potential functions, and in here, thanks. What we have is just the, so the potential functions really kind of live outside of our loss function. Thanks for catching this. And so before I was kind of thinking in terms of like identity, just so that I could talk about them with two different, I wanted to be able to talk about Z and also the potential functions, but this makes more sense. So now the potential functions actually live outside here. These are the potential functions. And they are the input to our loss. Does that make more sense?
It does. But just to understand what Z is a probability distribution over Y's given the X.
No. So the probability distribution over the y's given the x is represented by these marginal probabilities that are the output of belief propagation. So the z's allow us to, they fully specify that probability distribution, meaning what we're about to do is write down for a specific case, we're going to write down the derivative of a potential function here. And so what we'll need to do is, so for an MRF, we would have the log of the probability of y. Okay. And this log probability of y is fully specified if we know what those potential functions are, right? So this log probability of y for an MRF is just going to be a sum over all the factors, alpha, where for each factor, we're going to multiply together psi alpha of y alpha. Oops. With the addition that we actually need this to be the log of these potential functions. Okay. And then we're going to have minus the log of z of z. So if we wanted to define this for a CRF, it would look just about the same, but it would be log of P of Y given X is equal to a sum over the factors alpha of the log of psi alpha, Y alpha, and all of X, the quantity minus log Z of X. Okay. So if you know what the potential functions are, then you can write down what the probability is, but you might not actually be able to compute what that probability is because computing the partition function is NP or sharp P hard. Okay, so in our picture, at the moment that we have computed Z, these potential functions, we have everything that we need to compute the partition function and the joint probabilities, but we haven't actually computed those until we run the leaf propagation. Okay, so here is just the log probability written out. And now what we're going to do is we're going to compute the derivative of this log probability with respect to Z prime, which is the log potential functions. Okay. So we'll say we want the derivative of log of P of Y here. Now I'm actually going to work with the MRF case just because the CRF case is identical, it just includes a bunch of conditioning on X. So it'll just kind of clean up our notes a little bit if we write it this way. So the derivative is going to be with respect to the log of psi alpha. And here's where we need to be very careful. So remember that what we're actually doing here is computing the derivative with respect to some y alpha prime, which refers to a specific entry in that factor table. So if we go back up to our picture here, what we're actually doing is, say, taking the partial derivative with respect to, say, just one of these little factor table entries, like that red one. And so when we write out this derivative, we're looking at, on the numerator, a y that refers to the ground truth. Okay. So that log P of y is with respect to whatever we actually observed. And then by contrast, in the denominator, we have this derivative with respect to y prime, which is just sort of indexing into the factor table. And we're going to take derivatives with respect to every single entry in Z prime. Okay, so what do we do here? Well, the first thing we're going to do is we're going to write, we want the partial derivative with respect to log of psi alpha of y alpha prime of our MRF likelihood. So this is going to be a sum over alphas. Oh, and let's actually be a little more careful here. We're going to want a sum over, say, factors beta, right? Because we've already let alpha refer to one of the specific factors that we're taking a derivative with respect to. So here, this summation is going to be over factors beta, and for each one, we're going to have log of psi beta of y beta, where here, this y beta is referring to the ground truth from our numerator. Okay, so then we also need the minus log z term as well. All right, so what's the derivative of our first term here? So we're going to have the derivative of, with respect to log psi alpha y prime alpha of this summation. And what would that be?
We'll only get the derivative at the point when beta is equal to alpha?
Yeah, so it's only gonna kick in if alpha is equal to beta. That's right, and there's another condition that needs to hold. Have an idea?
The ground truth is 1.
Well, it's not that the ground truth is 1, it's that the ground truth, y beta, needs to equal y prime alpha for alpha equal to beta. So we could write this as a little indicator function, just saying that it's going to, the derivative is going to be value 1 if and only if the ground truth, y alpha, is equal to the thing that we're taking the derivative with respect to, which is y prime alpha. So conceptually, this is simple. This is just a sum of a bunch of terms, right? And in fact, if you look back up at our picture, right, if we're taking, say, to compute the log likelihood, what we did was we multiplied together the values from the different factor tables, and they were this blue value and this blue value and this blue value and this one and that one. So in this case, these blue values correspond to some assignment to y1, y2, y3, and to get the actual log probability, what we're doing is just adding up those log factor values. That's the numerator of the log probability. Okay, so in this case, if we're taking the derivative with respect to that red value, it's just going to be 0 because it didn't even show up in the numerator of the log probability. If instead we took the derivative with respect to, say, this lower corner that was blue, then it's going to, for the numerator, have value 1 as long as we're taking that particular cell. Okay. All right, so now, question.
So why does y alpha have to equal y alpha prime?
Because alpha is just telling us which table we're looking at, and y alpha prime is telling us which cell we're taking the derivative with respect to. So another way that we could have done this, we could have done this with like matrix calculus. In that case, we would have been taking derivatives with respect to log psi alpha, the whole factor. Okay, so that at this point, then we're talking about a matrix derivative or a tensor derivative, I guess. And so I didn't want to talk about matrix calculus, I just want to talk about partial derivatives with respect to real valued numbers. And so to index into the tensor psi alpha, I need to say which entry in that table we're talking about. And that's what y prime alpha is telling us.
So y alpha is the table and y prime alpha is the value of the table.
That's right.
How can they be equal? It's like I said, they equal the value of the table.
Sorry. Oh, I see what you said. Sorry. No, what you said is not true. So psi alpha of y prime alpha is a value in a table. So, sorry. The circled yellow part is a value in a table. The green highlighted part here, y prime alpha, is indexing into that table.
So the y alpha and y prime alpha are just the indexes?
They're an assignment to the actual values of the variables involved in the factor alpha.
So it only updates when you correctly assign the values?
Well, remember that we're going to take, so to get a gradient, we need to take the partial derivative. Okay, so think about what the gradient, so remember what we set out to do here was take the gradient with respect to, z prime. So z prime is all of these. So I need the partial derivative with respect to that entry, and that entry, and that one, 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 and that one. Right? I need every single partial derivative. Okay, and so we're just right now we're just writing out how to compute the partial derivative for one of those cells, but you're going to actually compute them all, and that would give you back this yellow highlighted tensor derivative. It's not even a tensor derivative is an okay way to phrase it with respect to z prime, which is all of those numbers. So the eventual gradient that we're computing here is going to have the same shape as z prime. So we're just computing one of those cells. Okay. So if the index of the ground truth, or the assignment to the values in the ground truth, is equal to the assignment of values corresponding to the factor entry that we're currently asking about the derivative of, then we get 1, otherwise we get 0. Okay, so now, what do we need? We need the derivative with respect to this log psi alpha of y alpha prime of the log of the partition function. So to take the derivative with respect to the log of the partition function, we're going to run through a couple steps here. So the derivative of the log of z with respect to the log of psi alpha. Actually, let's do something even simpler here. So let's write out one more step, which is, so we have this indicator function and then y alpha equal y prime alpha minus, and before we even figure out what the derivative of this partition function is, we can just apply the chain rule here, because z is also a function of the potential functions, or z prime. So here we can actually say, just apply the chain rule directly, and we would get some new term here. What would we get back by applying the chain rule? So you can think of this as like derivative with respect to some x. And then this is like the log of f of x.
So it's 1 divided by c with always the derivative with respect to c.
Yeah, exactly. So it's just 1 over z times the derivative with respect to that log of psi alpha y prime alpha of z, which is a function of potentially this and a bunch of other table entries. Okay, so now let's just compute the derivative of z with respect to that log of the psi alpha y prime alpha. Okay, so to get this, we just first substitute in z here, and we're going to have the derivative of the log of psi alpha y prime alpha of a summation over all the possible values that the vector y could take on. So let's call that y double prime. Okay. So for all of the possible assignments to all the y variables, we're summing over those, and for each one, we're going to multiply together all of the factors. So it's, in this case, not alpha, but we'll use again that index beta. And for each one, we'll have some psi beta of y double prime beta. So now we just need to take the derivative for the sum, and the first thing that we're going to do is we'll find that we can kind of throw out a bunch of the values of y prime that we don't care about. So namely, the only terms in the summation where this potential is going to be used are those for which y prime prime alpha is equal to, oops, sorry, let's say that this is y prime prime such that y prime prime alpha is equal to y prime alpha. So taking the sum over this restricted set is fine because for all of the other ones, we can't have possibly used this log potential function. It didn't show up in that product. So now we have the derivative corresponding to sort of two groupings of the actual terms in that product over the betas. So namely, we have a product over all betas not equal to alpha, or psi beta of y prime prime beta. And this whole product term is going to be constant with respect to the actual value of alpha or the value of the potential function that we're concerned with. And the value that we really care about is only going to show up in our second term here. Which is going to consist solely of the actual psi alpha of y prime prime alpha. Now, we can actually make one more observation here, which is because of the restriction in our summation here, we actually know that this y prime prime alpha is equal to y prime alpha. Okay. All right, so how are we going to get the derivative of the log of this thing when we're taking, this is like derivative with respect to log of x of x. So how can we get that to work? All right, let's make a side note here. So suppose you have derivative with respect to log of x. Then we can just say that this is equal to the derivative with respect to log x of log of x. Because exp of log of x is just going to be x. Syncing today. Okay, so here's our little side note. So the derivative with respect to log of x is just the derivative of, with respect to log x of log of x. And what's that? Well, that's just what is it? Yeah, it's just x of, so it's x of log x, right, times the derivative of log x with respect to log x, which is just 1. So in the end, we just get back that this is just x. Okay. So what that means is that this derivative can just fold this term, allows us to fold this term right back in to our summation. Okay. So this whole derivative term is just psi alpha of y prime prime alpha, or psi alpha of y prime alpha, since they're equal. All right, so finally then, we can just rewrite this whole derivative as a sum over all y prime primes such that y prime prime alpha is equal to y prime alpha. Taking the product over all possible factors beta of psi beta of y prime prime beta. So what we have here then is that the derivative that we were originally after is it's just sort of one step away from what we just wrote up here. So specifically, let's zoom out a little bit. So what we want here is the final substitution of what we just came up with back into the original derivative with respect to the log probability. And what we get is an indicator function of y alpha equals y prime alpha minus something beautiful. Let's see what emerges in the second term when we substitute back in this quantity. So here what we're doing is we're summing over all the possible variables except for those that participate in the factor alpha. Yeah, this is just the marginal, well, so this is not the marginal, but over here we have a 1 over z term. So if you take this and divide it by z, then we get back exactly the marginal probability of y prime alpha, which is insane. And so what we're left with here is so what we're left with is an indicator function on whether the current cell entry that we're looking at showed up in the numerator of the log likelihood for this training example, minus the marginal probability of the current cell. So think about what this is actually trying to do. If the current cell shows up in the log likelihood, then this gradient is going to try to push the log potential larger, which would essentially be pushing it closer to 1. If the value didn't show up, then this indicator function is 0, and it's going to try to push it in the negative direction, which is effectively trying to reduce the marginal probability for that particular assignment to the variables. Okay. So, I guess the last detail here is just that you can do kind of all of the same math except with respect to not the log of the potential, but the potential itself. And what you get back is essentially the same thing, except that you need to divide out the actual value of the potential, because we're no longer taking its log.
Could you go back to?
Yeah.
So when we write down the loss for a ground truth at the beginning of the derivation,
Yep.
we sum over beta for log psi beta y beta, right? Why aren't we taking a product over there? Overall beta. Like, shouldn't we consider all potentials?
So do you mean right here?
At the beginning of the derivation. Like when you're writing sum of
Yep.
beta log psi beta.
Oh, so maybe it's worth writing out. So remember what the actual definition of the probability is, right? Because this here is the log probability. But so this is the log of p of y. But if we wanted to write out, say, p of y, then what we would have is that the probability of y is a product over all, say, factors beta, where we take the product of each beta, y beta, and divide the whole thing by z. So essentially, what we're seeing here is just what you get when you take the log of that p of y. And I happen to switch from alpha to beta just so that we could index all of the factors. We could have this product go over all of the factors and then not conflict with the alpha that we're using to say which factor we're currently taking the derivative with respect to.
In the second last equation where we have vector of alpha, where did that part disappear?
Let's see. So in the second part, we had a derivative with respect to this part?
Yeah.
Oh, so why did this, so notice that this was a product over all beta except for alpha.
Yeah.
So I pulled out one of the terms that was corresponding to alpha. Okay. So that's this term. And so the derivative with respect to all of these, well, they were just a constant multiplying times the thing that we were taking the derivative with respect to. So these just pulled out as a constant. And then here, we took the derivative with respect to alpha, which we found this whole derivative to be psi alpha of y prime prime alpha. Well, that was just the missing term from this product. So I just folded it right back in, and now the product is over all beta. So this is actually the beautiful, this step right here, this is sort of like why all of this works. Like, this is the magical step. And the fact that this works is what allows us to get back that marginal probability in our final answer. And so what's fascinating about this is that something emerges which is incredibly powerful. Okay? So to run backpropagation, with a, say, log likelihood module, all we need are two things. We need to know how to do the forward computation. So the forward computation is just going to be the actual computation of log of p of y, right? Which we said is the log of, this product over beta, so psi beta, y beta, divided by z. Okay? So this numerator term is trivial to compute, but the denominator term is what we would say compute with belief propagation. Okay, but at the end, what do you get? You just get a single number, right? This is just a real valued number that you return from the forward computation. Okay, so what does the backward computation look like? What I mean here is the backward part of the backprop, right? You need to compute the derivative of log p of y with respect to the derivative of the log of psi alpha y prime alpha. Oh, thanks. So we need to compute the derivative that we just spent all this time on for all values of alpha, and then respectively for all values of y prime alpha. But doing so, okay, is going to just be some indicator function of the true value of y alpha and whether or not it equals y prime alpha minus that marginal probability of y prime alpha. And where do we get marginal probabilities? Well, again, we can compute marginal probabilities with belief propagation. So actually, I use chalkboards when teaching other classes. I opted not to for this one because of the online section, but it's maddening to have technology fail on you. Okay, so all I wrote here was, I rewrote the derivative and just am highlighting the fact that this you can also compute with belief propagation. So imagine a module in PyTorch. How would you implement such a module? Well, the first thing you would do is you would take as input all of your potential values. Right? The actual values for the potential functions are what you feed into this module. Once you have those, so you'll have that, you're also going to need the ground truth. And when you have the potential function values and the ground truth, you can run the belief propagation algorithm on the corresponding factor graph. That will give you the partition function z, as well as all of these marginals. At that moment, of course, I should throw in the caveat here. You never actually want to compute z itself. You usually want to compute log of z. And so you'll notice in our homework assignment that we actually ask you to implement belief propagation not using multiplication and addition, but using log add and addition, which is just a convenient way of reparameterizing the actual computation so that you're not multiplying together a bunch of probabilities such that they underflow. So once you can compute the partition function or the log partition function, then you can store that, and at the same time you will have just computed all of the marginals as well. So you should store those as well. Okay. You'll get back the output of the loss function, which is the log probability, and now you need to pass the adjoints or the derivatives with respect to the inputs to this module back to where they came from. Okay. To do that, all you need to do is compute that partial derivative with respect to each of those log factor values and hand that gradient back to the thing that computed them. And so, so the result is a fully functioning module that's just like any other loss function. that takes some inputs in, and it knows how to compute the output of the loss and also the gradient with respect to the inputs. Okay, so this is an incredibly powerful idea because here we said, okay, we're going to compute these with belief propagation. But we're going to spend a bunch of time this semester thinking about all sorts of different approximate inference algorithms. And so if you wanted to, you could just write a general purpose module here that takes some black box inference algorithm that knows how to give you either the partition function or an approximation to the partition function, and the marginals or an approximation to the marginals. And as long as you have that black box inference algorithm, you can use it within this PyTorch module. Okay, so now let's actually see how you might piece this all together in some examples. So let's start with a classic one, which is this combination of a neural network and a hidden Markov model. And so we had talked about sort of Markov random fields, and then we had also mentioned that there's this thing called a hidden Markov model, which is just like this Markov random field over a linear chain of variables, except that it has this restriction because it's a Bayes-net that the conditional probability tables sum to 1 across the rows. And so, so this is just another Bayesian network, and maybe the interesting property about it is that it reuses the same conditional probability table for emission at every time step and for transition at every time step. Okay. So what we can do, and what Yoshua Bengio did back in 1992, is we can think about a discrete HMM state. And here we're going to be thinking about phoneme outputs and continuous HMM emissions. Okay, so here, note that the Y's are actually the emissions in this particular model, and the S's are the hidden states. Okay, so usually we talk about Y's as the hidden states, but it's a little bit different just for this example. So the joint probability according to the HMM is given by this product of all of the corresponding conditional probability table entries. And the interesting part is we're going to assume that the probability of a particular Y, given its hidden state, is given by some Gaussian emission. Okay, so this is just should be a multidimensional Gaussian distribution over some vector yt. Okay. And the notion of hybrid here comes from sort of this idea that you could say that the actual emissions themselves come from the output of a neural network. Okay. And you could do this for every time step, so that each of these vectors, y1, the vector y2, the vector y3, and so on, comes from a vector of these y's, and the input to that neural network was the original audio signal that we're going to try to convert to a sequence of, say, characters or phonemes, like you did in homework 1. Okay. So there's a whole lot of things that just, like I can imagine this paper coming out in 1992 and everybody just like thinking to themselves like, what on earth? Because there's like this huge clash of visual notation. So the graphical model that we're talking about here is a Bayesian network. And so the arrows that we have in that graphical model are pointing from the top down to the emissions. But so that's the actual generative process for any Bayesian network, is to start at the root and gradually generate down to the leaves. By contrast, the neural network starts at the bottom and generates up. Okay, so the weird part about this is that in this case, the observations of the HMM are not actually observed. Okay? Right? The X's are the actual speech audio features as input. So essentially, what we have to do here is step back and now think of what we just did, which was to say everything that we're doing with these factor graphs we could think of as just a fancy loss function. And so we could say that there is some neural network that gives us emissions. And then those emissions are input to some loss function that is based on not a Markov random field probability distribution, but a Bayes-net probability distribution. Okay? So it works out all to be the same, though, from the perspective of inference. So if you want to compute the log probability for an HMM, what do? You multiply together all of the table entries. Likewise, if you want to compute the partition function for an HMM, well, you could run belief propagation, and you would get back that the partition function is just 1. You can also run belief propagation, and if you do so, it'll be called the forward-backward algorithm here, just because this particular model is a linear chain model. And so what we can do then is run belief propagation to get marginal probabilities, which here are denoted by gamma, for every hidden state variable. And the log likelihood then is given by, basically, in this case, if you know the forward-backward algorithm, it's given by alpha and t, though we also could have just written that this is given by sort of the output of belief propagation, right? The sort of standard numerator divided by the z that you compute in belief propagation. Okay. So you can essentially say that the decision function that you're using in this hybrid neural net HMM combination is essentially just some really complex differentiable function. And we can differentiate it easily because we just saw how to take the partial derivatives with respect to factors. Okay, and then our loss function is just the log likelihood. Okay. So, okay, I guess I have some slides here that are kind of summarizing what we just talked through, right? Which is just that how do we compute the actual gradient here? Well, you could think of this as dividing into two, dividing your function y of x into two parts, right? One is the part g that computes the graphical model log likelihood, and the other is the part h that computes the actual output of the neural network. Right? And the chain rule allows you to combine these together. Okay. So then you just need to figure out how do you actually compute these partial derivatives. Well, if we want to compute the neural net partial derivative, then we're just going to use some convenient automatic differentiation library like PyTorch. And if you want to compute the partial derivative for the graphical model, well, we just did it on paper and you could go and implement it. Okay. So, and just in case you forgot, this is a simple neural network like the one that Bengio was using, and it also has some forward computation and some corresponding backward computation that allows you to backpropagate gradients through it. Okay, so in the end, what do we get? Well, the neural network is going to sort of build up from the bottom, right? It's going to take some x's as inputs, and that will give us our first hidden layer of z's, and then it'll take the z's and we'll use those to compute our y's. And then given the y's, we'll run the belief propagation algorithm, and the output will be the marginals. And also, one of these alphas is going to be the actual partition function, z. Okay. And at the end, we'll just, it's not the partition function, it's the total probability of the actual sequence that we observe as. Okay. Okay, so we can call that our objective function, and now we can just proceed with the backward computation. Okay, so here we need to compute the partial derivative with respect to all of the emission parameters of the graphical model, and with respect to all of the outputs of our neural network, the actual Y's. And then we can backprop further all the way down into the parameters of the actual neural network. And at that point, we actually have the gradients that we need, and we can update the parameters of the neural network appropriately. Okay, so this is an age-old experiment where he was doing phoneme recognition. This was speaker-independent recognition of plosive sounds. So these were just and actually I don't know does anyone know what DX is? I don't speak IPA. So these are all the HMM hidden states, and then so those were the actual S values, and then the metric was just accuracy. Okay, so he was looking at 3 models: a neural net only, a neural net plus an HMM, where you're training the 2 completely independently, and then putting the 2 together, jointly training them. Okay, and what you see is that the neural net does honestly pretty badly, but if you combine it with the hidden Markov model, it actually then does pretty well. And why is that? Well, it's because we know that there are really strong correlations between successive phonemes. Okay. And then finally, if you put the neural net together with the HMM, and train them jointly, back propagating through the whole thing, you get a big improvement still. Okay, so oh yeah.
Why would you not train an HMM on the X's simply? Like, why would you prefer training them on Y instead of X's? Like,
why would you?
why are we using the neural net in the first place? Can't we just build an HMM that takes X as the input and then predict the next state?
Oh yeah, so he is kind of missing a baseline here, right? Which would be something like just an HMM, right?
Right.
And there should have been some other bar here that we don't have. So that's absolutely the right thing to do. The catch is that you would probably do really poorly, and the reason is that you would somehow essentially need to align input frames to output frames. And I actually forget now exactly how he was going about that, whether this Bengio paper was actually assuming that you knew the number of outputs a priori. So this might have been sort of a cheating experiment compared to what you guys were doing in homework 1, where you could have your output be arbitrary length. He might have actually been restricting the output to be the true known length of the output. Not 100% sure. Otherwise, if you don't do that, you have to worry about actually alignment. And really, at that point, this isn't just an HMM, it's actually a finite state transducer. So anyway, yes, so he should absolutely have had another baseline. I'm not actually sure how well that would have done. Okay, so that was with sort of a standard feed-forward neural network, but you could also imagine setting up almost exactly the same thing, but using an RNN and an HMM. And essentially, so there's this paper by Graves that uses sort of a deep bidirectional LSTM, and then each hidden unit is an LSTM cell. And it was deep, right? It was actually more than just 2 layers here. Yeah.
So if you look at this diagram, Y has incoming edges from the top and from the bottom, which means that the 2 parts are knowing why they're dependent, they're conditionally dependent.
So Y has, are you saying the Y in the RNN and the Y in the HMM?
They're actually disconnected here, but in the previous diagram,
Yep.
they were the same, right? When we had this one.
Mm-hmm.
So Y1, Y2, all the way until the end has incoming edges from the HMM and from the neural network.
Yeah, and so the reason that I redrew this as a factor graph is because conceptually I think it's actually better if you think of this as, it's actually easier to think of this as not an HMM but a CRF. Because if you think about it as a CRF, then what this is giving us is just some conditional probability, which is the probability over these states, S, given some Y. So the actual probability distribution that we care about is that conditional distribution over states given what we typically call the observations of this linear chain. Okay. And if you know what the x's are, then these observations are a deterministic function of those x's. Okay. So essentially, we do actually, if you know what the parameters of the neural network are, you know exactly what those y's are. And then the actual graphical model is just giving you a conditional distribution over S given Y. Okay, so as it happens, an HMM actually gives you a joint distribution over S and Y. And so that's why in the actual definition of the HMM, we needed to say that the emission distribution was Gaussian. Because at the end of the day, we actually are getting technically we're getting a joint distribution over Y and S. Okay, but the Y is essentially just a deterministic function of our true input X. So right now, maybe I can drop a slide in about this next time. The current state of the art for pretty much any sequence labeling task that you could care about tends to be where the number of outputs are sort of a fixed sequence, tends to be a CRF LSTM, which is sort of analogous to what we're about to talk about here, which is an RNN HMM. And that would be the case where we're explicitly modeling some conditional distribution of the states given the Y's. And so, so anyway, in this case, the model inference and learning can be sort of analogous to this neural net HMM hybrid that we just looked at, where the objective function is log likelihood, the model is this combination of HMM with Gaussian emissions, inference is forward-backward, and learning is stochastic gradient descent with backprop. And so, so again, this sort of combination of models is able to do better. So here we could also think about taking, say, a convolutional neural net and combining it with a conditional random field. And so to do that, we would say that, in a standard CRF, each of the factor cells is a parameter, right? A transition or an emission parameter. So in the hybrid model, these values are actually computed by a neural net with its own parameters. Okay, that's the picture of the LSTM CRF that we drew originally in our notes. So we're going to run some convolutional neural network that is going to fill in these table entries. And then we'll run some inference algorithm to actually get a partition function and marginal probabilities. Okay. For computer vision, the CNN would be in 2 dimensions. For natural language, the CNN would be 1-dimensional. So here, the sort of earliest example of this was this 2011 paper by Colvert and Weston, where what they were saying they were doing was a neural net plus this sentence level likelihood. Sentence level likelihood was just their way of saying a linear chain conditional random field. So they basically, this picture is now flipped. Their neural network worked from the top all the way down to the bottom, and then the output was used as a factor in a distribution over the hidden states. And it also gave the values for the unary factors as well. Oh, sorry, no, this is a separate model. So the neural net with word level likelihood was where there were no transition factors. They only had unary factors. So this is sort of an uninteresting model. And what they found was that for all of these different tasks, there was some improvement when you incorporate the actual transition factors into the model. And that's the SLL over the WLL. Okay. So, so if we look back at the current state of the art for all of these tasks, they're all using embeddings like BERT, which are these sort of contextualized word embeddings, and then those are fed into not a CNN CRF, but an LSTM CRF. And that's essentially the state of the art right now for all of these tasks. So as well, you can do interesting things like pose estimation, where say your model might be a deep CNN plus some MRF. And again, if you do joint training of these things, you end up getting better performance on all of these. Okay. So I'll skip that and say, I'll skip that summary and say one more detail here, which is, so minimum Bayes risk decoding is sort of the key for how we actually then get back our predictions from the model. And the minimum Bayes risk decoder is going to return the variable assignment with the minimum expected loss. And so what we care about for your homework assignment is saying that we want to minimize the Hamming loss. And so across this, this syntax labeling problem. And so the minimum Bayes risk decoder is just going to return for every variable, its prediction for that variable is just going to be the y hat, or y hat I, that maximizes the marginal probability for that variable. Okay. And so next time, what we'll do is we'll look at a different minimum Bayes risk decoder, which is returning a vector y hat that maximizes the total joint probability of all of the variables at once. Okay. So this is, once you actually know what the marginal probabilities is, this is just sort of returning variable level argmaxes. And this problem, solving this argmax over all possible assignments to the variables y is NP hard, and we'll think about next time how we can use linear programming, integer linear programming to do it. Okay. All right. See you guys then.